John Napier, who invented logarithms, Henry Briggs, who first discovered them with Napier's help, who brought them to England. It never occurred to these people to do this. Taking an object like logarithm, like sine, like cosine, like square root, and turning it into a function is a profound idea, which was not done in mathematics until about 1750. It was Leonard Euler in his Introductio in Analysis Infinitorum who finally had this wonderful idea of taking sine and cosine and square root and logarithm and making functions out of it. If you don't like functions, this is probably not exciting to you. Couldn't he have left well enough alone? Do we need functions? It turns out they're way easier than the old way of doing it. Math used to be far harder than it is. We can be grateful this is here. So this is a function. It's a wonderful thing. Be grateful for it, for my sake. Please. If it's a function, what can we do with it? We can graph it. Let's try this. What does the base b log of x look like? I think we just set up coordinate axes here in some way. Am I close? I'm not even close. You'll forgive me if I try to use the new technology. There we go. Alright. Thank you very much. We can find what log base b of x looks like. We can easily set up coordinate axes like so. Your calculator, of course, can give you a better rendition of precisely what this is. We can come fairly close just with our pen. Picture should look something like this. It will turn out to be the case, and you might be able to figure this out for yourself, that the x-intercept is always at 1. This is the point 1, 0. Logarithm will keep getting bigger and bigger as x gets bigger, but it grows very slowly. It looks almost like a straight line for big values, and eventually it's almost straight. It does, however, keep getting bigger. The domain takes it all the way up to infinity. Eventually log will get as big as we want it to get. Alright, that's it for the big ideas. This is what a logarithm is. What can we do with them? What sort of questions might we ask? How do we solve logarithms? How do we analyze them? How do we think about them? This is where we need to turn next. So let's try it. Example 1. Let's start with something that looks like a very difficult question, but turns out to be fairly simple if we can think about this the right way. The question is this: which is bigger? We mentioned first grade earlier. This should remind you of first grade. Do you remember seeing the 4 and the 7 next to each other, trying to put a less than or a greater than sign between them? How about this? Which is bigger? The base 4 log of 18 or the base 8 log of 60? The question sounds tricky. How can we know which is bigger? To calculate these precisely is hard. We'll find a way to use calculators to do these precisely, but what can we think about? Well, think about this. The base 4 log of 18 says that 4 to some power is 18. What would you raise 4 to the power of to get 18? Well, I know that 4 to the power of 2 is 16. So, whatever this is, and maybe I don't know it precisely, whatever this is, it must be more than 2. How about the base 8 log of 60? Can you think of 8? Is 8 to some power equal to anything you can think of as sort of close to 60? Well, yeah, I think, once again, we know what 8 to the power of 2 is. 8 times 8 is 64. If 8 to the power of 2 is 64, then 8 to the power of something less than 2 must be 60. So this is less than 2. We don't need to know what they are to analyze them. I know immediately this must be bigger. This number is bigger than 2. If you can get to the point where you can look at this expression, the base 4 log of 18, if you can look at this and say, you know what, I think that's a bit bigger than 2, because I know that 4 squared is 16, you're in a very good place. You can think about logarithms in this way. It'll be very much easier for us to work with it. Let's try a second example. This is an example that we'll be able to turn into a problem we did just a few sections ago. I want to find the base 4 log of 8. Let's find what y is in this expression. Well, pause for a moment. We're getting better at logs, but they're still a bit new. Perhaps the easiest thing to do is take a logarithmic equation, base 4 log of 8 is y, and turn it into an exponential one. This is a thing we practiced for so long earlier. Well, we know this means exactly the same thing as 8 is equal to 4 to the power of y. It doesn't imply this. This isn't some sort of mathematical deduction. This is another way of writing exactly the same thing. If 8 equals 4 to the y, now can we solve for y? Yes, we did this a few sections ago. This is the sort of exponential equation that you possibly learned to hate. But if you know that both of these numbers, 8 and 4, are powers of 2, we can rewrite them easily. 2 to the power of 3 equals 2 to the 2 to the power of y, which means 2 to the power of 3 equals 2 to the power of 2y. And now, since both of these are exponents of the same base, since this is both 2 raised to some power, it must be the case that 3 equals 2y, and therefore that y is 3/2. I will also tell you, if you don't like solving problems this way, there's a much easier method using logarithms. Wouldn't it be ridiculous if the only point of logarithms was to take them, translate the problems into something you've already seen, and then solve it? Yes, it would be terribly ridiculous. There are better ways. Logarithms will help us to make problems like this much easier. We'll get to that tomorrow. For now, let's look at one more useful example, and it's a domain example. What do we do if we want to find the domain of a logarithm function? Well, we haven't talked much about domains and ranges of logarithm functions, so let's get some brief information. First, if we take a function like the base b log of x, we know some things about it. Its domain, the values that it can take. Your domain, your dominion, your domicile is where you live. Where does the function live? What x values can it take? Well, it can take any positive x value. It can't quite take 0, but anything bigger than 0 is okay. What we hold in our head here is that only positive values are permitted. What else do we know? The range of the function. We saw what the range of the function was, at least we briefly mentioned this earlier when we drew our picture. The range of the function is all possible real numbers. Anything between negative infinity and infinity is permitted. So what do we know about logarithms? They have to be positive. Why? Why must they be positive? Well, if you take, let's see. If the domain is a positive number, that means the values you're allowed to put in for x here must be positive. Could you put in a negative number and have it be okay? Let's say b is 10. 10 raised to what power is, let's say, negative 5? If I ask you for the base 10 log of negative 5, remember what that means? That means that 10 raised to some power equals negative 5. How many times should you multiply 10 by itself to get negative 5? There's no answer to this question. 2 isn't enough, 100 isn't enough, you can't do it negative 6 times, that doesn't work. There's no answer, this is simply not possible. You can only put positive numbers into logarithms. Given this information, let's find an explicit domain. What if I want the domain of something a bit more complicated? Let's ask for the domain of the base 3 log 18 minus 2x. All we think about is this. There's something here inside of a logarithm, and I know that must be positive. We just said this. The logarithm of something only makes sense if that something is positive. So we must have, the only possible thing here for us is that 18 minus 2x is positive. It must be greater than 0, and if it is, this of course reduces to a problem that we're very good at and have solved many times before. We find that x must be less than 9. What else might we need to know about logarithms? Let's think about, for a minute, what we can do. We talked about different bases of logarithms. Here's a new question. What's the best base for logarithms? Base 10 logarithm might make sense. We use a base 10 number system. The base 10 logarithm tells us lots of nice things. It tells us, for example, how many digits a number has. If you want to know how many digits are in 9,316,000,008, ask for the base 10 logarithm, round up, you'll get the answer every time. Maybe the base 2 logarithm makes more sense. We know a lot of things come in twos. Computers count things by twos. Maybe that's nice. It turns out there's one more natural yet. I think I've never met a student who believes me when I tell them this, but it turns out the best, the most elegant, the easiest, the most natural base of logarithms is the following. It's a logarithm base 2.7182818284590, and we could keep going for a long time. In fact, the most natural base is one that never ends. It's a number a little more than 2.7, and it's one that goes on and on. This number might look familiar to you. Perhaps you've seen this before. This is the log base e. E is this magical number in mathematics, second only to pi in its applications and how often it turns up and the number of things it can do. E is a fantastic number, and it turns out it's really, really good at doing logarithms. There are a lot of reasons for this. Only one are we going to talk about today, but first let's look at what this means. Because we have something called the base e log, because it's so natural, we have a name for it. This is so natural, we call it, and we call it exactly what you hope we'll call it, the natural log. The natural log is ln. ln. Why ln? Why not nl? Wouldn't nl be a better abbreviation for natural log? Well, like so many things in mathematics, this came first from the Latin, it came first from the French, and if you've taken Spanish classes or French classes or Latin classes or Italian classes, you remember the adjective comes after, not before, the noun, right? La casa grande, the logarithm natural, ln, is the natural log, so apologies to English speakers everywhere. We're stuck with the notation, it's too late to change. What do we know then about natural log? What if I ask you for the natural log of e? Again, remember what this means. The natural log is the log base e. So if we look at this question, we should say to ourselves, e raised to some power should be e. What is that thing? E raised to what power? Well, 1, right? Any number raised to the power of 1 is itself. The natural log of e is just 1. How about the natural log of e to the 4th power? E raised to some power should be e to the 4th. Do we know what that power is? Of course, it must be 4. E raised to the 4th power is, in fact, 4. In fact, even better, the natural log of e to the x is always equal to x for the same reason. That's what natural log means. We might even note one more, the natural log of 1. The natural log of 1 is the same as the natural log of e to the 0. You've seen already that anything raised to the power of 0 equals 1. You've seen why that's true. I hope you've seen why that's true. If not, hurry off to your nearest Google-ready device and ask why this is true. There's a very good reason for it. The natural log of e to the 0, just based on what we've done before, must be 0. The natural log of 1 is equal to 0. What's so natural about it? Why is it so important? I'm not quite going to tell you yet. Let's do one more example first, and we'll get back to it. Final example, using the natural log, and it will be this. Solve the equation, e to the power of 3t minus 4 is equal to 1,000. This is one of those equations that makes students groan. Who cares? Who cares? Why would we do such a thing? I will tell you, this looks very much like things we will see soon.